Let's say we have some hydrochloric acid and a solution of sodium hydroxide. We know that hydrochloric acid is a strong acid, and so we can think about it as consisting of H plus and Cl minus. Sodium hydroxide is a strong base, so in solution we're going to have sodium ions and hydroxide anions. Let's think about the products for this reaction. Well, one product would be H plus and OH minus. If you put H plus and OH minus together, you form H2O. So water is one of our products, and the other product would be what's left over. We have Na plus and Cl minus. So that gives us NaCl, which is sodium chloride. So this is an example of an acid-base neutralization reaction where an acid reacts with a base to give you water and a salt. So in this case, our salt is sodium chloride. Let's think about an aqueous solution of sodium chloride. So you take some water and you take some salt and you dissolve your sodium chloride in water to make your solution. So in solution, you're going to have sodium cations and chloride anions. And let's think about what those would do with water. So we know that the pH of water is 7, right? So the pH of water is equal to 7. Now, sodium ions don't react with water, right? So they're not going to affect the pH of our solution. And you might think that the chloride anion could function as a weak base and take a proton from water. However, that's not really going to happen very well because the chloride anion, right, Cl minus, this is the conjugate base to HCl. And we know that HCl is a strong acid, and the stronger the acid, the weaker the conjugate base. So with a very strong acid, we're going to get a very weak conjugate base. And so the chloride anion can't really take protons from water very well. And so the pH is unaffected. And so the pH of our solution of sodium chloride is equal to 7. And when you have a salt that was formed from a strong acid and a strong base, right? So sodium chloride was formed from a strong acid and a strong base, right? These salts form neutral solutions, so your pH should be equal to 7. Let's compare this situation to the salt that's formed from a weak acid and a strong base. So over here we have acetic acid, which we know is a weak acid, and then we have sodium hydroxide, which is our strong base. So in solution, we would have Na plus and OH minus. Right, so hydroxide is going to take the acidic proton on acetic acid, and this is the acidic proton on acetic acid. So once again, H plus and OH minus give us H2O. And let's think about the salt that forms here. If you take a proton away from acetic acid, right, you're left with acetate. You're left with CH3COO minus, the acetate ion. And we also still have sodium ions here. So the sodium ion could ionically bond over here with your acetate anion. All right, so here we formed sodium acetate. And let's think about an aqueous solution of sodium acetate. So we know that the pH of water is 7. Right? And let's think about what we have in solution. So once again, we have sodium cations, which aren't going to react with water, so that's not going to affect the pH at all. But the acetate anions will. So let's go ahead and write out what would happen. So the acetate anions are going to react with water. So let's think about what would happen here. So let's put this at equilibrium. The acetate anions, right, we know this is the conjugate base to acetic acid. So this is going to function as a Bronsted-Lowry base, and water is going to function as a Bronsted-Lowry acid. Water is going to donate a proton to the acetate anion. So if the acetate anion picks up a proton, we would form acetic acid, CH3COOH, right? So just add an H plus to the acetate anion. And if the acetate anion takes a proton away from H2O, if you take an H plus away from H2O, you're left with OH minus here. So what has happened in our solution? Well, the fact that the acetate anion is present, right, has increased the concentration of hydroxide ions in solution. So we've increased the concentration of hydroxide ions. So the pH is no longer 7, right? We've increased the pH here. So the pH should be greater than 7. So an aqueous solution of sodium acetate is going to have a pH of greater than 7. And so in general, this is true. If you have the salt, this salt here that was formed from a weak acid and a strong base, these salts form basic solutions with pHs greater than 7. All right, let's look at one more example, and this is the example of a strong acid and a weak base. So HCl is our strong acid, and ammonia is our weak base. So HCl is H plus and Cl minus. We're going to donate a proton to NH3. So if NH3 accepts a proton, it's going to turn into NH4 plus. So this is ammonium. And then we also have some chloride anions. So that would ionically interact with the ammonium. So we form ammonium chloride here. So this is our salt. Let's think about an aqueous solution of ammonium chloride. So once again, for water the pH is 7, and the chloride anions aren't going to affect the pH. But the ammonium ion will, right? So NH4 plus will react with water and affect the pH. And so let's look at the reaction. So NH4 plus H2O, right? So what's going to happen here? Well, the ammonium ion is an acid, right? It's going to function as a Bronsted-Lowry acid. It's going to donate a proton to water. So water is going to function as a Bronsted-Lowry base and accept a proton. So if you take away an H plus from NH4 plus, you're left with NH3 or ammonia. And if you add an H plus to H2O, then you get H3O plus or hydronium. Right? So what is happening in our solution? We've increased the concentration of hydronium ions, right? We've increased the concentration of hydronium, and we know that what that's going to do to the pH, right? Our pH is no longer going to be 7. We're going to decrease the pH. And so we have an acidic solution. So the pH is now less than 7. So an aqueous solution of ammonium chloride is going to have a pH of less than 7. So a salt that's formed from a strong acid and a weak base is going to give you an acidic solution.